Another important aspect of basin retrofit potential is the storage volume of the basin. There are several ways to find a basin's volume. If you have access to a particular basin's plan sets, these will most likely contain design drawings, details, and calculations that will be able to provide you with the storage volume. This is the quickest and most convenient way to find a basin's volume. If you don't have access to these plans for whatever reason, you can use GIS to calculate an estimate for the basin's volume. Today I am using ArcGIS Pro for this demonstration, but these calculations can be done in any iteration of ArcGIS or ArcMap software, or open source GIS like QGIS. First, you need to have a DEM, a digital elevation model, which I have right here. Turn it on for you really quickly. This DEM that I am using is from OGRIP. And then from the DEM, we are going to create contours, which I already have made right here. So let's turn them on and get started. We are going to find the volume of this basin. The first way we are going to calculate the volume for this basin is by using geoprocessing tools that are found in the 3D Analyst and Spatial Analyst extensions in ArcGIS. If you don't have access to these tools, we will be covering another way to calculate basin volume in the second portion of this video. The first thing we are going to do for the basin volume calculation is to create a polygon that represents the basin footprint. You can trace the edge of the basin visually, like this way, but I find it simpler to just use the uppermost closed contour in the basin as the template for the footprint. So we'll be using this contour right here. All right, now we have our basin footprint polygon. In order to turn our DEM into a surface that can be used to calculate the volume of the basin, it needs to be converted to a tin. A tin, or a triangulated irregular network, is another way to represent a surface where the surface is represented by triangles. As you can see in this guidance document provided by ArcGIS, you can see how the surface is made of triangles. To do this, we run the raster to tin tool in 3D Analyst. I found that in order to create a tin that represents the input DEM as closely as possible, put your Z tolerance to a very low number. I'm using 1 in this example. This will ensure that the difference between the input DEM and the tin is minimal. The other inputs right here and here can be left as their defaults. Here is the resulting tin. See how the surface is represented by triangles? You can see how they form a continuous surface. And if I turn off our basin footprint, you can see how you can make out the basin in the tin. Now we are going to assign elevation data based on the tin to our basin footprint polygon. To do this, we use the 3D Analyst tool, Add Surface Information. Our basin footprint file is our input. We are only calculating the surface information for one basin footprint polygon in this example, but the Add Surface Information tool will calculate the surface data for however many polygons are in your input file. Then our tin is our input surface. Okay, and we will be calculating the minimum Z, the maximum Z, and the mean Z for our basin footprints. And Z in this case is just our elevation. So we're calculating the lowest elevation within our basin footprint, the maximum elevation within our basin footprint, and the average elevation across the whole basin footprint. Now we run it. Our Add Surface Information tool has finished running, so let's open our attribute table. So our attributes for Zmin, Zmax, and Zmean have been calculated. Our Z max is at 1,184.8. And now that we've added our surface information to the polygon, we are going to use the tool Polygon Volume. This tool calculates the volume between the basin footprint polygon at a given elevation, which in this case we're going to be using Z max, and our input surface, which is our 10. And it's important to make sure that our reference plane is calculated below the plane. What this does is the volume and surface area are calculated below the reference plane height of the polygons. This will ensure that we calculate the volume between the basin footprint at our maximum Z and our input surface below. Polygon Volume has finished running, so let's open up our attribute table. This tool has calculated a volume of 154,789 cubic feet. Another way to calculate the volume of a basin is to use contours to calculate the stage storage. Using this method requires contours, and the basins whose volumes you are calculating need to have closed contours. Without closed contours, this method won't yield very accurate volume estimates. To start our stage storage volume calculation, I'm going to start at the contour above the highest closed contour, which in this case is 1,185, right here. What I'm going to do is, starting at our top contour, 1,185, I'm going to trace around the contours to create polygons. When you get to the end of the first contour, the one that isn't closed, you finish drawing the polygon by visually connecting the dots, if you will, to create a closed polygon. This area right here, where the elevation above the highest closed contour is the closest, is the overflow point of the basin. So if this basin were to overtop, the first place the water would start to spill out is right here. So now that we have our finished top contour, I am going to trace around all of the basin's closed contours to create polygons at each of those elevations. For any elevations where there might be more than one area of closed contours, like at 1,183, I just draw around the areas so as to encompass them in the final polygon in order to represent one continuous polygon at a given elevation. The same can be said for elevations that might have distortions from the DEM, like at 1,180, how there are these big triangle cutouts. I try to create a smooth polygon to represent the surface area at that elevation, as it would be in real life. Now that we have finished drawing the polygons at each elevation, let's make sure to assign the correct elevation to each of them. Now I've gone ahead and added an elevation field to the file so that I can easily just enter them in. And I always calculate the surface area of the polygons in a separate field to ensure that it's calculated in the correct units and in the correct coordinate system. In this case, we're using square feet, and we're using our Ohio state plane. And when you're finished drawing the stage storage polygons for all of your basins, go ahead and export the attribute table as an Excel file so that we can continue our volume calculation. Now that we have our attribute table as a spreadsheet, I'm going to delete these columns and add an ID column and a notes column. We are going to go ahead and label this basin as Pond 1. Next, I'm going to sort the entries from the lowest elevation to the highest elevation. Since the contour at elevation 1185 was not actually closed, we need to add a new row between 1184 and 1185 to represent the elevation at 1184.5. This will serve as our top of basin for this calculation. We're doing this because 1185 isn't a closed contour for this basin, which means that it can overtop any elevation between 1184 and 1185. So our elevation of 1184.5 serves as an approximate top of the basin for this exercise. In order to interpolate the surface area at the elevation 1184.5, I'm going to take the sum of the elevation at 1184 and 1185 and then divide by 2. This gives us an approximation of the surface area at this elevation between our two known elevations. Now I'm going to add columns for incremental storage and cumulative storage. In order to calculate incremental storage, we are going to input this formula. The area at the higher elevation plus the area at the lower elevation divided by 2 times the higher elevation minus the lower elevation. And we're going to calculate the incremental storage for the whole basin to our approximate top of basin volume. Now that we have incremental storage between each of our elevations, we are going to calculate cumulative storage, which just means we're going to add up our incremental storage. What we're going to do is we're going to add our lower cumulative storage, which for our lowest elevation will be 0. We're going to add it with our incremental storage at the higher elevation. Then we will do that until the top of our basin. Our stage storage calculation has given us a volume estimate of 154,517 cubic feet. Now, if we compare that with the volume that we calculated using our Polygon volume, that was 154,789.9 cubic feet. So there's only a few hundred cubic feet difference between the two volumes. Our two separate volume estimates match pretty well, but it's important to note that the precision of your stage storage calculation will depend on the quality of the contour file that you use. If the interval between contours is too large, you won't be able to estimate the basin volume very well. I would recommend using at least 1-foot contours if you have access to them. 2-foot contours can be used in a pinch, but 1-foot contours will yield a higher quality estimate of the basin volume.